Here in section 10.3, we are introducing polar coordinates. So in this particular coordinate system, we're going to be looking at identifying points in the xy plane with two coordinates r and theta, where r is the distance from that point to the pole. So you imagine drawing a line segment from the point P to the point O. O here represents the pole, but in our case, you can think of this as the origin, the point 0, 0. And then the other coordinate in polar coordinates is the angle theta that it makes with the polar axis. What's the polar axis? Well, the polar axis is just the positive x-axis. So by identifying our point P with these two coordinates r and theta, we're creating our polar coordinate system. And we can also think of the angle theta here as a negative angle. So you could, for instance, have the angle theta go in the counterclockwise direction, the clockwise direction. Positive angles go in the counterclockwise direction. Negative angles go in the clockwise direction. Similarly, if I have a negative r, a negative value for the radius, we imagine that our point would be on the opposite side of the angle theta. So if I'm looking at the point r theta here, a negative r value, a negative coordinate here would be flipped onto the opposite side of the angle r. So you imagine extending r to the opposite angle. So it would be the same distance r away from the origin, but on the opposite side of the angle. So let's just practice plotting points in polar coordinates. The first point, 1, 5 pi over 4, has a radius, a value of r, 1. That means it's 1 unit away from the origin, and makes an angle of 5 pi over 4 with the polar axis. So where would that angle land? So to first think about where does the angle 5 pi over 4 land, we're going to imagine rotating around our coordinate plane here from the positive x-axis to the angle 5 pi over 4, which is going to be right down the middle of quadrant 3. Okay, so drawing this angle here looks like that's telling us now where the angle 5 pi over 4 is going to land there. And then where does the point 1, 5 pi over 4 land? Well, it's going to be 1 unit down this line. So imagine breaking this line up into distances. Let's say 1 down that line, that's 2 down that line. The point 1, 5 pi over 4 lands right there. Okay. So it's a point right down the middle of quadrant 3. Where does the point 2, 3 pi land? So in this case, we can imagine our point 2, 3 pi is going to be a distance of 2 away from the origin, and it's going to make an angle of 3 pi with the polar axis. So if we revolve an angle of 3 pi, that's going to go around 1 complete rotation, that's 2 pi, but then it's going to go 1 more half rotation. So that's where the angle 3 pi is going to land. So really, we're looking at a point that's going to land here on our negative x-axis. Okay, and then we go 2 units down the negative x-axis, and that's where that point is going to land. So in polar coordinates, the point 2, 3 pi will land right here on the negative x-axis. Notice that this is the same as the point 2 comma pi. So there are multiple ways to represent a point in polar coordinates. So here we're representing it with an angle that's more than 2 pi, but if I were to represent it here with an angle that's plus or minus 2 pi from that angle, we'll land at the same position. Similarly, I could also express this with a negative angle. For instance, the angle 0 would be the positive x-axis. So if I do negative 2 comma 0, it's going to land at the same point there. So negative 2 comma 0 would land right there because it's at an angle of 0, but it's on the opposite side of that angle. What's another way we could write it? I could also write it with a negative radius negative 2 and an angle of 2 pi, because that's going to land at the same angle as angle 0. And then a negative 2 flips it to the opposite side. And we can continue. It's possible to generate multiple different variations of this as well. So we can actually see there are infinitely many different ways to represent a point in polar coordinates. Let's try one more, where now we're given a negative angle, negative 2 pi over 3. Where does that angle land? So since it's a negative angle, we're going to go in the clockwise direction to locate it. And 2 pi over 3 is going to be in this quadrant here. And it's going in the negative direction. So it's clockwise from the polar axis. And then we're going to go again 2 units down that line. So that point will land 2 units down the line at negative 2 pi over 3. Is there another way I could represent this angle? So the angle negative 2 pi over 3 could also be written as a positive angle if we were imagining going in the counterclockwise direction. I could write it as the angle 4 pi over 3. So I could also represent this point as 2 comma 4 pi over 3. It'd be the same point. So you see again here there are multiple ways that we could represent a point, and that's always true. And then the final one here is looking at the point negative 3 comma 3 pi over 4. So now it's got a negative radius. So let's think about where this point might land. Since it's an angle of 3 pi over 4, that's going to take us to an angle here in quadrant 2, right down the middle. However, because it's got a negative radius, we're going to be on the opposite side of that angle. So if we extend that line onto the opposite side, we're going to get a point now in quadrant 4. So the angle 3 pi over 4 is going to land in quadrant 2, but because it's got a negative r, we're going to land in quadrant 4. Okay, so now again we're going to go 3 units down this line. That'll take us to the point negative 3 comma 3 pi over 4. How would I represent this point with positive radius, with a positive value for r? Well, one way would be to just think about what angle this is. For instance, I could locate this angle by adding pi to the angle 3 pi over 4. So that would give me an angle of 7 pi over 4. So another way I can represent this point is with the radius of 3 and an angle of 7 pi over 4. And like we saw in these other examples, there could be infinitely many other ways to do this. For instance, I could do a negative angle, or I can add 2 pi to this angle and it'll bring me back to that same angle again. In order to convert between polar coordinates and Cartesian coordinates, we can imagine the geometry of polar coordinates, thinking of how they relate to this triangle. So one thing to remember about Cartesian coordinates, sometimes these are called rectangular coordinates, is that we're measuring the location of a point x comma y in terms of its location on the x-axis, a certain distance down the x-axis. So the x-coordinate there represents, of course, its location on the x-axis, and the y-coordinate would represent its location somewhere on the y-axis. So then we can imagine that those correspond now to the legs of this right triangle, where r in polar coordinates represents the hypotenuse of that right triangle. And then the angle theta represents the angle at the base of the right triangle. So with this, notice that we have a very simple trigonometric relationship between the angle theta and then the sides x, y, and r. Because we know that, for instance, sine of the angle theta will equal to the y value here. Or I should say the sine of the angle theta will equal to y over r, the opposite over hypotenuse. So therefore y is equal to r sine of theta. Cosine of theta will be x over r, so x is equal to r cosine theta. Now that gives me two equations that can be used to convert from polar coordinates. So given an r and a theta, we can use these equations to convert that point into Cartesian coordinates. Okay, so that gives me the x and the y coordinate given an r and a theta. Similarly, if I'm given an x and a y, we can use Pythagorean's theorem here to figure out what the radius r is. Because of course we know that it's a right triangle, so x squared plus y squared equals r squared. So that gives me a way now to find r given the x and the y coordinates. And given given the x and the y, we can find the angle theta using the tangent ratio. We know that tan of theta is going to be the opposite over hypotenuse, opposite over adjacent. And so tan of theta will be y over x. Okay, so that gives me now a way of finding the angle theta in terms of x and y. So let's practice converting. Say I want to convert the polar coordinate 2 comma pi over 3 into Cartesian coordinates. Okay, so you can imagine here, it's going to be a point here somewhere in the first quadrant, where it makes an angle of pi over 3 with the polar axis, and then it's a distance of 2 along the hypotenuse. So to find the x and the y coordinate, well, we can just use the basic right triangle trigonometry here. X is going to be 2 times cosine of pi over 3. Cosine of pi over 3 is 1/2. So it's 1. And the y coordinate would be 2 times sine of pi over 3. Sine of pi over 3 is radical 3 over 2. So it's just radical 3. Okay, so in Cartesian coordinates, this point would be the point 1 comma radical 3. Let's practice going the other direction. Here I have a Cartesian point 1 comma negative 1. Where would that land? So I have a point here, 1, -1, that's in the fourth quadrant. To find r, we can use Pythagorean's theorem. You know, r squared is x squared, r squared is x squared plus y squared, so r is the square root of x squared plus y squared. So putting in our x and our y coordinate there, we get square root of 2 for r. So that would be the distance down this line here. Now let's find the angle. There's many ways we could do it, but let's consider one way would be to do the positive angle here. Or another way would be to use the negative angle measured that way. We know, for instance, now that if that angle is theta, we know that tan of theta is going to equal to -1/1. Which means that here we can do this in a couple ways. Theta equals tan inverse of -1 will give us a value of -pi/4. So it's going to give us the negative version of that angle. However, if we're going to use a positive angle, we can also express that angle as positive angle 7pi/4. So in polar coordinates, the point 1, -1 will be square root of 2, -pi/4. Or you could write square root of 2, 7pi/4. Or there could be many other different representations, but these would be perhaps the easiest ones to use.